Okay, so our next speaker is Professor Simon Lucas, who is a professor of artificial intelligence at Queen Mary's University of London, where he is the director of the Game AI Research Group. The main focus of the research is the intersection of AI and games, where he explored how games can serve as an ideal testbed for AI research, as well as how can AI be applied to create better game playing agents, generate new games, and optimize game content and parameters. The research involves studying various types of machine learning within a particular focus on reinforcement learning and evolutionary algorithms. And today he's gonna talk to us about simulation-based AI. So the floor is yours. I think this is not working. You can start. Yeah, no, it's gonna have to be the mouse, I think.
Okay.
But for some reason it's not working. Oh, actually it does work.
Good. Is the audio okay? You hear me okay? Great. Thanks for inviting me. It's a pleasure to be here talking about my favorite research topic, actually, which is simulation-based AI. This is something I've been doing for quite a while now, probably about 15 years, I guess. And it's something that I think is more relevant and more exciting now than it ever has been. And one of the reasons for that is the amazing progress. So it's a little bit funny. Can you hear like an echo myself? Sure. I could just try holding it. Yeah, so I think the what you can do now with LLMs, for me, the superpower of LLMs is coding. They're amazing at writing computer programs really quickly, especially if what you're doing is at all close to any kind of textbook algorithms that exist somewhere. You know, this just mined the whole of the internet and all the great textbooks on computer science and AI. And so we have the possibility now of developing algorithms for things like simulation-based AI faster than we could before, and also for developing little bits of them. So I also use ChatGPT and things in what I teach. So I teach a course on further OOP, for the object-oriented programming, and I encourage the students to use ChatGPT as well and say, yeah, you can use this for your assignments too. And the challenge there is to set things that are tough enough that ChatGPT can't do it yet. And I think it's kind of a moving goalpost right all the time. So yeah, that's a bit of the sort of background to this, but I think it's a very exciting topic. And one thing I think about generative AI, so I didn't really get into using LLMs and chatbots. Yeah, I wasn't into GPT-1 or 2. I didn't really start using them until 2 years ago when ChatGPT really hit the internet. And I just thought, wow, this is amazing. And I was interacting with a regular kind of thing and giving it programming challenges. And I found very often that it's sort of new stuff, but you had to kind of tease it out. So if you write it, ask for a classic algorithm, very often it'd be quite lazy and give you an inefficient one first. And you say, well, can you do better than that? And it said, oh, yeah, you know, I didn't know I had to. Oh, well, you actually want an efficient one. You want a logarithmic one, not a linear one. And it can do amazing stuff. Yeah. Oh, well, yeah. I've got various theories about why it's lazy. So sometimes I think it might want to save on compute power. So you look at the millions of people interacting with it, and if it costs like 10 times in compute every time for a query, when it doesn't really need to be that good, then it could be a compute thing. Various other possibilities too. Yeah. So what I've noticed, so I use these things really, really regularly, normally multiple times a day. And I think that despite the amazing progress, I sort of feel like they've plateaued a bit. And I also find that my personal experience of this is kind of at odds with the progress in benchmarks. So the benchmark in this field is a nightmare, right? And if you look at the latest O1 preview from ChatGPT that does so-called thinking, so it's slower now than the previous ones. And if you interact with it, it'll say, okay, thinking, analyzing this, and it does a kind of chain of thought thing. And it might take 10 or 20 seconds to give you a response instead of like 1 second that ChatGPT would do before that. And sometimes it's a bit better. But on one of the benchmarks, which is graduate student questions, it improved from something like 13% for GPT-4o up to about 78%, like an amazing level of improvement. And my experience with that, I thought, well, you know, you're not much smarter, like a tiny bit. So how we benchmark these things is also important. And I always say to people, you know, it's what you need to do with it. And that's what really matters the most. So my take on this is that simulation is the key to making these things smarter. So they've got amazing knowledge in them, and they can apply it to situations which are certainly novel to them as well. So I can give it a programming problem that's got to interact with an API, like the rest of the software that I've written, that for sure it's never seen before, it's never seen these names, and it's a whole sort of new structures. And it will produce software that I think, bloody hell, that's amazing. You know, you've written something, you couldn't possibly have seen this before, and yet you've written something that's kind of sensible, and often it's quite good. And yet we'll see some problems in a minute for which it's completely hopeless. Even the latest O1 preview, completely hopeless. But for anyone in this room, they'd handle it easily. And I think the key to making them smarter is simulation. So it's like, you know, as humans, we have imagination, and we're able to kind of think of things and think of consequences of things and do some sort of kind of planning. And that's really the essence of what we're talking about. So I think, and by the way, when I say that the progress in generative AI, I think has plateaued a bit, I'm really talking about the models themselves. What I think is not plateauing at all is the whole kind of ecosystem. So if you look at the challenge of building systems that use these, and one of the great things about ChatGPT is the whole system is really good. So they spend a lot of time engineering the system. And if the underlying model is not, it may not be better than Google's model, but the engineering they put into the system is really good, and it gives you that kind of satisfying outcome. And I think simulation is really the key to this. So at that kind of high level intro, we're going to kind of dive into a bit more details now on some of this. I hope some of it's not too detailed. I also want to plug for, so I'm head of the Game AI group at Queen Mary, and one of the things we do is a tabletop games framework. The reason I've kind of spliced that in here, this is an open source project on GitHub. We also have a spin out company. But TAG has more than 20 games, really complex ones, like if anyone's played Terraforming Mars, some of the tabletop games now, they're just incredibly complex. So they come with dice, cards, tiles that you lay on boards. They're just super complex. They're amazing. And they're so far beyond the state of what we can do with AI to play to a really good human level. But we have some general simulation-based AI that kind of can play many of the games at some sort of novice level. So what is simulation-based AI? I mean, hands up who knows Monte Carlo tree search? So I know this is a multidisciplinary group, right? So only a couple of you. It's a really cool algorithm. You've all heard of AlphaGo and AlphaZero and all this stuff, and the deep reinforcement learning behind it. But the other half of that is Monte Carlo tree search. So it doesn't just learn how to act in the moment, right? It does a kind of tree search of future possibilities, rates those possibilities, and acts based on that. So that's already using simulation. But the idea is really simple, right? So simulation-based AI, we have a forward model of a system. So that could be a game, it could be I don't know, like a taxi routing service where you're simulating cars going around a city and getting stuck in traffic and things. You just need a simulation. And what you do to make decisions with simulation-based AI, you consider lots of possible alternatives. You know, the idea is incredibly simple, really. Some of the algorithms are complex, but the idea is simple. You just consider lots of possible alternatives, and you pick the action that's going to lead to, most likely lead to the best outcome. And if you want to model games with multiple players, you assume that the other players are also doing similar things. Yeah, that's the idea of it. The amazing thing is that you can start with random actions or random policy, and often that still works quite well. What DeepMind did with AlphaGo and AlphaZero, that they learned really good state value function. So a state value function is you look at, for example, the chessboard or Go board, and you say, well, that's really favorable to white or black. You also have policy functions. With a policy function, you say, given this situation, what are the likely moves that you might make? And then we'll explore those more deeply. We're now going to simulate those. We're going to do rollouts. and explore these more deeply. But yeah, that's the main idea, really. So here's one of the things I like as well. It's quite explainable. So these are kind of anytime algorithms. So you run them for as long as the time you've got, and you get a decision. So what we're doing, we often think of evolution as a slow process, but here we're doing evolution in the loop. So all those kind of pink lines that you see, they're evolved random action sequences where we're evolving to play the game of asteroids. Hands up who doesn't know asteroids or know nothing about it. Yeah, many of you, right? You got to get down the arcade and play it. It's a really good game. So the algorithm playing that doesn't know it's playing asteroids. It just knows that it's got a forward model that it can do random rollouts of an action sequence, and it'll get a score by the end of that sequence. And all it's going to do is run evolution to say, well, okay, what about if I do something different here, and here? Is that going to make it better or worse? And if it makes it better or certainly not worse, then we're going to accept a new sequence and then evolve from that. That's the basic idea. So this gives us a type of AI that's immediately tunable. What you saw, if you're watching really closely, in the first asteroids video, the action sequences were really short. So those pink lines are quite short, and it crashed, didn't do very well. So we make those longer, make it more far-sighted. So we're simulating further into the future, and it does better. So yeah, the good thing about this is that we get kind of sensible behavior, even quite good play across a range of situations without having to train for that particular scenario. We're just saying, here's a new model, deal with it, do your online evolution, and do some sort of sensible behavior. It's also interesting that the random rollouts lead to good play because we're completely reevaluating all the time, right? So we've got a plan of what we're going to do, and each time step, we're just going to take the first action off that plan, add a new random one to the end, and then re-evolve it every time. So all the time, we're adapting. And if our knowledge of the world changes, fantastic, we just put it into the model. If the rules of the game change, we learned something really quite new, fantastic, we just put it in the model. No need to retrain. So if you're in the mood for an algorithm, and who's not, let's be honest. This is the algorithm. This is, we've got many algorithms. This is the simplest one, and it's one of my favorites. So this is it, really. We start at the start of the game. We've got something called best sequence. This is our plan. This is what we're going to do. And we just make a random action sequence of length L, say 100 actions in the future. And then for each decision in the game, we say, okay, the best sequence now is a shift and random append of what we've got so far. We shifted because we've already used the first action, right? And then for a number of evaluations, we say, well, let's make a mutation of this sequence. So we're going to pick points on that action plan and just randomly change them. And if that is better than or equal to the previous best sequence becomes mute sec, and we just carry on doing this for n evals, and then we return the best option each time. That's it. You understand the algorithm there. I just thought I'd throw in this. I only saw this yesterday. This is a talk that Noam Brown gave a few months ago. If you don't know the name, he's at OpenAI now, applying simulation-based ideas to what OpenAI do with ChatGPT. But he became famous in AI because his work led to the superhuman poker play. So he developed Libratus and Pluribus, which beat some world champions in poker. And that was a really big challenge. And the reason I'm talking about it here is this graph, and he gives a great talk on this, and there's a link to the YouTube video. But he's talking about with and without search. Before he applied it to poker, people were doing poker just with neural networks and pattern recognition. So training it on billions of hands of poker, but just a reactive neural network. And he thought, well, this is crazy. You look at the human players, and they're thinking about it, especially with complex things. They're thinking, for tens of seconds about what to do. And the neural networks were just responding in a few milliseconds. And he said, well, hang on, couldn't we do search? We could. He did. And developed world champion poker players. So this is another example. This is the same algorithm as before. And what you're seeing in the graph are the expected rewards 100 time steps into the future for different action plans. this is playing a game called Planet Wars. You might have it on your phone as a game called Galcon. But what you have to do is take over the enemy planets, and your opponent is trying to do the same thing to defeat you. And that's it. And that's just showing that it's also good at that. That's the same algorithm without retraining. So we've got a word game here, and that QR code, if you want to scan it, that should take you to a playable demo. But I just wanted to show a completely different example now. So this is a game I wrote called Griddle. I like playing it. It's a word game. Behind the scenes, there's a deck of about 80 cards that get shuffled, and then you get dealt one card at a time. This is a game partway through. There's only a few cards left to play. So it's a 5x5 grid. You're going to get dealt 25 cards. And each time you get dealt a card, you place it on the grid. You've got to place it in a way to make as many long words as possible. Well, as many words, but for example, the 5-letter words, they count for 10 points. So they're worth more. Now, a variation of that algorithm I just showed you can play this pretty well. So I'm quite a good player at this, and it can beat me most of the time. And I thought, wouldn't it be interesting to try all these versions of ChatGPT and Gemini to see if they can play it? And so I did that because, you know, they know about words. I thought they might be quite good at this. And so I describe it. This is a chat. This was an older version of ChatGPT. I did this about a year ago. But I've done it a few days ago with the latest O1 preview, and I get the same sort of results. So the interesting thing is it's very good at describing the game. I said, you know, first of all, I'll tell you the rules. Now just tell it back to me. I want to make sure that you understand it. It's fantastic. Yes, I understand the rules. Let's play. So I've skipped some bits out here. But we have nice, really encouraging chat. It understands the rules. It's going to place letters in favorable places to try to make good words. And then we play it, and there's a link to the kind of longer version of this. But all it does actually is place letters one at a time, left to right. And that's no better than random. So that's really, really poor play. And it can't play the game at all. And then a bit later on, it breaks down and it tries to extend the grid and make it bigger. So it's you know, really, really hopeless. And surprisingly bad because, yeah, I just find it interesting that if you talk about the rules with it, it gets it, but it can't actually put it into action. So here's another example. So this is simulation-based AI. This is for a maritime capture the flag competition. Yeah, so this is interesting because we've got a complex game. It's only 3 versus 3, but there are multiple units to control. And it's a game with a very large branching factor. So if you consider both your and your opponent actions, then there's like 17 to the power 6 actions at each time step. And so it's interesting to compare the SBAI compared to RL for this. And so this is slowed down at the moment. So this is think back to the asteroids and those lines were where the ship expected to be. What we're doing here now, we're plotting the plan lines for each boat that we're evolving all the time. And then at the end of it, we're showing the expected reward. And I just want to go back a little bit because to begin with, you notice all those rewards, there are a few sort of round numbers like 0, minus 1,000. And then at that point, it changed. At that point, we turned on the heuristic. So a heuristic function in this context is we're going to look at the state of the game. And rather just saying, well, you got 0, you haven't scored anything yet, or you got minus 1,000 because you just crashed into one of your own boats. It says, well, yeah, it's much more nuanced. And then what you see is that this is now beating the team over here, is a very defensive team that actually won a recent tournament on this at AMAS 2024. And we're now scoring points and playing the game successfully, just using this simulation-based AI, but with a heuristic function that was partly written by ChatGPT. So that's, yeah, one of the things I'm saying is that there's a great opportunity to link what we do in the rest of AI with LLMs. And it's really, really powerful when you link it in this way. And yeah, there's more of the same really. I don't really need to show the other video. Interestingly for this, it's sufficiently hard that in this competition, none of the RL methods perform very well at all. And one of the things that I'm pushing about SBAI is that the simulation model supplied for this was really inefficient. And actually, one of the biggest pieces of work I had to do was to actually rewrite the simulation. And this is the sort of thing that LLMs can also help us do to do things more effectively. Yeah, so I think I'm approaching being out of time, but I think simulation is really a superpower for AI, and it gives us explainable AI. We can run simulations, and we say, well, why are you recommending this course of action? And we say, well, because we've simulated it a zillion times, and these are the statistics of the outcome. You know, we can model all these uncertainties, all these other factors. And the simulation is really key of this. Things like the running speed, the approximations you make, the fast copying, the sampling over uncertainties. And what we want to do now is to give the AI agents more control over the simulation, to actually decide which bits of the complex world are you going to model for this part of the decision. And I think that, yeah, especially of interest to this meeting, is I think that's quite human-like as well, in the way that we approach problems. You know, all the time we've got a really complex world to deal with. And part of the skill of being good at doing things is to say, well, I'm going to ignore those bits of the world, and I'm going to focus on what's relevant to the current task. And that's something that's really kind of lacking in these simulation-based methods at the moment. They tend to just say, well, here's a world model. I'm going to advance it forward using the kind of standard interface, the kind of standard action space. And we need more sophisticated ways to say, well, I'm not going to bother simulating all of this. As an AI agent, I'm going to say these things are the relevant things, and I'm going to focus on that. And yeah, so I think it's like a great time to be in simulation-based AI, and LLMs can definitely help writing the heuristic functions and writing the simulations, and leading us to ever better AI. Yeah, that's my talk. Thank you.
Definitely. Thank you.
Thank you.
So given your version of the interesting, I wonder whether the heuristics is something like metacognitive, or can you think about them as a metacognitive kind of understanding the task, as you said, or what do you think is in those heuristics that make them much better?
Yeah, I hadn't given a lot of thought to I mean, you're talking about metacognition, right? In AI, we talk about meta heuristics, and I think there's a kind of overlap between the two. So when we talk about meta heuristics, we talk about kind of beyond regular heuristics and ways to generate heuristics and way to use heuristics. And I think there's a similarity in that sense. So, for example, when I got ChatGPT to generate the heuristic function for the capture the flag, I fed in the rules, and I fed in the rest of the API, and I said, now do this. And I guess the and it was actually, can I just say two things about it? One thing is that it did a really good job when I looked at the code. I thought that's really sensible. That's kind of what I wanted to do, but couldn't be bothered to do myself. That's really sensible. And actually, it had got a sign the wrong way around. So the first one it came up with was like the opposite of good. And I thought, well, why is that negative? So I flipped it around, and then it was good. But I think for me, what's even closer to the metacognition level here is what I'm talking about at the end with the agent-controlled simulation API, where you say, okay, here's a big complex simulator. You know, we can simulate a ton of stuff. But now for the AI agent, which bits are you going to choose to simulate to make this decision? Because if you simulate everything that you could, it's going to be slow. And not only slow, but so much irrelevant things just added noise to it. Yeah, thanks.
Yeah, I did. Okay, so you done that side? I mean, okay, sure.
Thank you very much. I'm not very familiar with meta heuristics, but I did some research in like game theories and stuff. I guess you're familiar with like repeated prisoner's dilemma.
Yeah,
and stuff.
yeah.
So say that with you have a real player playing against an AI. Can simulation help them to build some sort of trust or cooperation based on simulating? Like say that the real player is a very cooperative person
Yeah.
versus a not very cooperative person. Yeah.
Yes, absolutely. So what you can do is build opponent models as you go through. There's quite a bit of work in that actually. So you can also look at you can also like have a catalog of likely models that you try to fit the opponent to. So you say, oh, okay, I think this guy's like a tit for tat type guy. All those sort of things. But yeah, that's the real thing. One of the things that's interesting as well is that you mentioned iterated prisoner's dilemma. There's an even simpler game, rock, paper, scissors. And they still have tournaments on RPS. And another interesting facet of this is that for all these kind of simple games, the Nash equilibrium is known. I say for all, I mean I'm oversimplifying a bit, but for some of them, you know the Nash. And actually, when they put in these competitions, Nash plays really badly. Well, not really badly. So it'll be if they have, I think the most recent study I saw had about 100 players, and the Nash equilibrium would be, say, 30% of the way down from the top. So by no means the worst, but by no means the best because they're unable to exploit poor behavior. And so as soon as you have an opponent model, you can do that with the risk that the opponent could be kind of tricking you and like pretending to be bad. And then all of a sudden, they turn out to be brilliant. And, they say, well, why didn't you bet more on this one or something? And then they save their best for last.
I guess so they can like learn to trust based on like trials and errors.
Yeah,
Ah.
yeah.
Thank you for a great talk. I was wondering, why do you think the performance is much better when you plan 100 steps into the future rather than planning for the near future? So as an incompetent human, I can't even imagine what it means to plan 100 steps ahead. Obviously, it could be good, but the degrees of freedom are enormous.
Yeah, you know what, that's a really great question, actually, because it's not always better. It's absolutely not always better. And you've got a trade-off between doing a short-term plan really, really thoroughly versus a long-term plan, which may be far from optimal because you've got so many kind of elements of the plan, right? You've got to, well,
The
you
variability
know,
is enormous.
yeah. The search space is absolutely vast. So it doesn't always do better. And actually, it's a hyperparameter of the system that has to be tuned. So it just depends. But in some cases, yeah, it just has to be tuned. There are other more sophisticated algorithms also that put more effort at the start of the plan as well. So you might still consider a long way into the future, but put much more effort into optimizing the early part. And this is something that I didn't go into details, but Monte Carlo tree search does that better. But yeah, I think definitely interesting though to consider things where you can see a long way in the future. And I think the other thing that within the community, I would say we don't do at all well, and it's something we should really do much more of, is much more hierarchical planning. So within the kind of traditional planning community, that is definitely a thing. But within our kind of simulation-based AI or kind of statistical Monte Carlo tree search type thing, we don't do enough hierarchical planning. So, I'm already thinking about how I'll get the train home later. And that's just a high level plan, I'll go to Liverpool Street and get a train according to the timetable. In that plan, of course, I'm going to make little steps all the way. And I'm not thinking about those, okay? So I think to do hierarchical planning within this kind of context is still really a challenge.
Thank you.
Is this it? Yes.
So in that game with the letters, so you explained, sorry, my voice is I'm losing it. So you said that you explained the rules to the AI, ChatGPT,
Yeah,
and it repeated it concisely and
Yeah.
clearly. And you said, well, that means it understood it, but it couldn't play the game.
yeah,
And I'm wondering whether maybe it didn't understand it, or like if it did understand it, what does that mean? 'Cause, like,
yeah,
of course, if I teach someone something and they repeat it to me in a clear, concise manner, and it's another human, I'm pretty sure they understood it. But maybe the AI didn't understand it.
yeah,
It's like repeating it to you in different words in a concise manner.
yeah. I mean, in a sense, it clearly, yeah, it gets the very nature of understanding because, you know, I think there are obviously different levels of understanding. You can understand something in the sense that you could explain it to somebody else in different language. So you have some sort of internal representation of it at maybe at quite a superficial level. But you can also understand something maybe quite deeply and still not be able to do it.
I think maybe that's the point. Like maybe it didn't do it because it can't, but maybe it didn't do it because it didn't understand it. Whatever.
I think it didn't do it because it doesn't have the right computational mechanisms. I think that's part of it. So what it comes down to is that I've got here in bold, LLMs are poor at planning. And that's why I think it's such a good match to put simulation-based AI, which is very good at planning, with LLMs, which are very bad at planning. So they're good at lots of stuff, but they're very, very bad at formulating plans and executing them. And I think that's the key to it, really. So what does it mean for it to so I think there's a difference between understanding something and being able to do it. And I think that's what maybe we're getting to the heart of.
Or maybe there's a difference between rephrasing something or summarizing something and understanding it, as far as
I think that's also true. Yeah.
Right, thanks again, Sam.
Thank you.